Welcome back to this course on blockchain and its applications. So, in the last class we have looked into the Bitcoin protocol and we have seen that how we can achieve consensus in Bitcoin by combining proof of work along with PBFT. And then while analyzing the performance of Bitcoin, we have seen that Bitcoin can achieve performance close to Visa, but for PayPal transactions where the typical transaction rate is 4,000 transactions per second, in that scale even Bitcoin cannot reach. So, we asked this question that how far we can go with a blockchain in terms of transaction scalability, and we have tried to look into or tried to revisit that what are the fundamental problems that we had in Bitcoin proof of work that was preventing us to reach into a scalable consensus architecture. Now, we will start from that point here today in this lecture, and we will learn a consensus algorithm which is really internet scalable, and that particular consensus algorithm is known as Algorand. So, today we are going to learn Algorand in details. So, the topics or the keywords that we are going to cover today, these are the methodology which is being used in Algorand, something called cryptographic sortition. So, we are going to learn what is meant by cryptographic sortition, and then we are going to learn about this B star mechanism which is used in Algorand. So, B star basically means repeated Byzantine agreement. We will see that how that repeated Byzantine agreement is used to help Algorand to achieve internet scale scalability. So, this is the point where we stopped in the last lecture. We mentioned about this performance triangle of a typical blockchain architecture, where we have a trade off between three parameters: scalability, security and decentralization. And our question was that is it ever possible to achieve all these three requirements simultaneously? Well, and in that context is work Algorand, it tries to solve this problem. It tries to make a balance between the scalability, security and decentralization, and it claims that it can achieve consensus in internet scale with certain magic or magical techniques in the system. We are going to learn about those magical techniques, and we are going to see that what magic Algorand does to solve this blockchain performance triangle to satisfy scalability, security and decentralization simultaneously. So, this Algorand, the idea of Algorand was first introduced by this paper, Algorand Scaling Byzantine Agreements for Cryptocurrencies, that got published in proceedings of the 26th Symposium on Operating System Principles, the conference SOSP. And the primary author of this paper was Gillard, Hemo, Silvio Micali, Vlachos, Zeldovic, and they were from the MIT Media Lab. And Silvio Micali, who was actually the core developer, one of the core developers behind Algorand, and who promoted Algorand as a kind of next generation blockchain fabric. And now Algorand is itself an enterprise who is trying to solve different problem, scalable blockchain applications with the help of this idea of Algorand. Well, so that way in different use cases people are planning to apply Algorand. So, it would be nice for us to learn that what magic Algorand does to scale up in terms of both number of nodes that can be supported, as well as the transaction per second, that is the transaction throughput, which is being supported by the underlying blockchain. So, if I just try to look into the overview of algorithm, the key idea is that it achieves consensus through Byzantine agreement protocol. Well, and the moment it achieves consensus through Byzantine agreement protocol, you know that transaction scalability is not going to be a problem. You can support large number of transactions because this Byzantine agreement it works really good in terms of supporting number of transactions, or it scales up with the workload of the system. The major limitation of Byzantine agreement, as we learned earlier, is the number of nodes that it support, and here we see that the magic that Algorand is going to do to help the system achieve this transaction scalability close to standard Byzantine agreement protocol, but with the help of a large number of nodes in the network. So, the communication media that it uses similar to Bitcoin, it is the gossip protocol, and the key assumption is the honest majority of money. Honest majority of money means the people who have more amount of Algorand with them, they are more viable to become a part of the underlying consensus mechanism. Well, so to participate in the system, you need to get hold of good amount of Algorand, good amount of money with you, so that you can prove that, well, I am a legitimate user in the system, and so I have done a lot of transactions in the system. So, I am a legitimate user to participate in the consensus procedure of the system. Well, but remember that this honest majority of the money, that does not put up any limitation in the selection of nodes who are going to generate the next block. Well, that different kind of technical advancements that are being done by Algorand are as follows. First of all, it uses some trivial computation. It uses simple operations like add, count, this kind of operations. It does not do any kind of complex operations, complex mathematical operations like finding out the nonce from the hash, which takes a lot of time. It uses an idea of true decentralization. It does not have any concentration of mining pool power. All users are equal, and everyone is treated equally. Well, so it is just like that. You need to hold a certain amount of money to prove that you have participated in the system, you are well equipped with the system, so that you can honestly participate in the consensus mechanism. Then one of the important aspect of Algorand is that it ensures the finality of payment. Well, so unlike the Bitcoin fork, the probability of fork in Algorand is very less. Well, so typically it does not like that the fork cannot happen in Algorand. Fork can happen in Algorand, but the probability of fork is very low. So, that way because the fork can happen with very low probability, the block appears and the payment is fixed forever. So, if you have a block, that means your payment is mostly fixed. Well, then it supports scalability. So, it can support millions of users only with the network latency, that means around 1 minute it takes to add up every block, and it provides security. So, it is safe against a bad adversary. So, because the fundamental principle that it uses is the Byzantine agreement protocol. So, as I mentioned that the question comes that what magic Algorand does to scale up the Byzantine agreement protocol. So, if you just try to look into the architecture of Algorand, it is fairly simple. So, first you select a random user. So, that random user will prepare a block and propagate the block through gossiping. Well, and when a random user is preparing a block and propagating the block through gossiping, you need to ensure that the block that have been proposed by that random user, that block is a valid block. So, the question comes that who is going to validate that block. Now, to validate that block, we again select a random committee with a small number of users. So, around say 10k users. So, 10k user is something like a small, because you are talking about millions of users in the network. So, we are not going to use all those millions of users to validate the block, rather we are going to select a subset of it. So, this random committee, it runs Byzantine agreement on the block that is proposed by the random user. If they agrees on the block's validity, then they digitally sign the result. They may use something like a collective signature, which we have already seen it is scalable enough, and it propagate the digital signature saying that, hey, this block is valid. So, it is something like that, one random user propose a block and then another random committee it validates the block, and that way the block gets propagated in the network. Well, this is interesting, right, because everything is random, the user is random, the committee is random. So, that way if you just participate as an attacker, you have fairly low chance to be a part of either that random user or that random committee, because your inherent assumption is that you have millions of users who are participating in the consensus procedure, and when you have millions of users, that means as an attacker your probability to get selected is 1 by million. Well, so that is, as you understand, it is very low. Well, and even if you are getting selected, you are proposing a new block, but that new block is getting validated by a random committee, and when the block is getting validated by a random committee, it will be difficult for you to ensure or to manage or to collude majority of the participants of that committee. Unless you are able to collude majority of the participants of that committee is not going to support your block. Well, so because of certain randomness and the inherent assumption is that, well, majority of the participants in the systems are honest, and that need to be, because unless majority of the participants in the systems are dishonest, then a society cannot run, right. So, that is the kind of inherent assumption behind any society, that the majority is good. Now, when majority is good, then the probability that a random user is getting selected who is going to propose a new block that is good is high, and at the same time whenever you are selecting some random committee to validate that block, it is with high probability that the members of that random committee majority are good and they are going to support that block. Okay. But the question remains that, well, we are good with this word random, we are using a random user to propose a block, we are using a random committee to validate a block, but the question comes that who is going to select that random committee? Well, because we are in a decentralized network, and in a decentralized network I cannot have any third person or a trusted third party who is going to select the committee for me. Well, now that is the most important committee, and here Algorand actually does the magic, and we are going to see that what magic it does. Now, to select that committee, the magic that Algorand uses, that idea is called cryptographic sortition. What is mean by cryptographic sortition? So, I asked this question that who select the committee, and the answer is that every individual user select themselves as a part of the committee. Okay. This sounds interesting and strange, right. So, that means I am going to select myself as a part of the committee. So, if I am going to select myself as a part of the committee, obviously I need to prove that I am someone who is eligible to be part of the committee. Well, how I am going to prove that I am eligible? Now, to prove that I am eligible, Algorand uses this magic which is called cryptographic sortition. So, what is cryptographic sortition? So, the cryptographic sortition is an algorithm that every individual participant runs, and this cryptographic sortition generate two things. Well, so, just like a kind of high level idea, let me explain it in this way, that cryptographic sortition returns two things. One is 0 and or 1. So, 0 means you are not a part of the committee, and 1 means you are a part of the committee. Well, so it generates this 0 1, but along this 0 1 it also generates a proof that the 0 or 1 has been generated. Well, so that means every member, whenever they are getting a 1 by running this cryptographic sortition, so that means it generates 1, and the proof, that proof actually says that 1 has been generated. Well, so the member who gets 1, say this member gets 1, this gets 0, this gets 1, this gets 1, this gets 0, this gets 0, this gets 0. So, the member who gets 1, they send that information through gossip. Well, so whenever they are sending that information through gossip, they are sending information that 1 and the corresponding proof, saying that this proof actually validates that, well, ultimately 1 have been generated from that cryptographic sortition mechanism, and that information is sent via the gossip protocol to all other members in the network. That way everyone understand that, well, at this round, say this member 1, member 2, member 3, they are the member of this my consensus committee. Okay. So, consensus committee means the committee that I was talking about earlier, who is going to validate the newly proposed block. So, let us see that what is this cryptographic sortition algorithm. Now, what is this cryptographic sortition algorithm? The cryptographic sortition algorithm works in this way, that each committee members, as I mentioned earlier, it selects himself or herself according to per user weights. Well, so this weight comes from the amount of money that individual users have, and this implemented using something called a verifiable random function or VRF. Well, so this is the magic that is being done. So, what is VRF? So, VRF takes this private key of the user, say user I is going to generate a VRF for it. So, it takes the private key, certain input message, well, we are going to see that what is this x, and it generate a hash and the corresponding proof. So, the proof is to validate that the hash that I am going to claim, that hash is correct. Well, so x is my input string, pki and ski the public private key pair. So, sk is the private key. So, the private key is used to generate the verifiable random function, and the public key is used to generate to verify the proof. The hash is the hash length bit long value that is uniquely determined by sk and x, and the proof is something that enables to check that the hash indeed corresponds to x. Well, now how the algorithm works? The algorithm works in this way. So, to select the committee member, every node it runs this cryptographic sortition mechanism. That means, it executes the verifiable random function with these parameters sk is its private key, certain seed. So, this seed is the publicly known random value. So, the seed that is published at Algorand's round R using VRF with the seed of the previous round R. So, this seed is also generated based on this verifiable random function. So, that way the seed value that is also uses certain kind of random number, but that is verifiable. Then I have a threshold. So, the threshold that determines the expected number of users selected for that role. So, for example, if I decide that, well, only one user is going to be selected through this verifiable random function, then my threshold is 1. If I am going to select that, well, I want to have a committee of 100 member. So, the threshold would be set 100. Then role, so the role basically determines whether this VRF is getting executed for proposing a block or for to be a part of the committee member. W is the weight of the user, and capital W is weight of all users. So, weight of all users that is known, that basically the total amount of an Algorand that is available in the system. So, it is the total amount of Algorand. So, the total amount of Algorand which is available in the system, that is known, and J is the user which gets to participate as one of the sub users of a part of the committee. So, the user runs this sortition mechanism, it returns this hash proof and J, and that way that particular information is used or as a proof that, well, I am going to be a part of the committee member. If it finds out that, well, the value J is non-zero, the value J is non-zero means it is the part of the committee. Well, if the value J is 0, that means it is not a part of the committee, and that way I have the hash and the corresponding proof, which is helping me to validate that I have run the cryptographic sortition mechanism correctly with the help of this verifiable random function, and whatever information that I am going to claim through this gossip protocol, that information is the correct information. Well, so this is the core idea behind cryptographic sortition, through which the committee members are getting selected. Now, once these committee members are getting selected, the next task is to run the Byzantine agreement protocol. Now, to run the Byzantine agreement protocol, what Algorand does, Algorand runs this Byzantine agreement in two phases. So, it is a basically two phase agreement protocol. It has something called a final consensus and another thing called a tentative consensus. So, let us try to see what is mean by final consensus and what is mean by tentative consensus. Now, before going to that, Algorand makes two different assumptions. Well, one assumption is in that it called as the strong synchrony, and the second assumption it is called the weak synchrony. So, what is strong synchrony? The strong synchrony basically says that most honest users, say 95% of the users are honest, can send message that will be received by most other honest users within a known time bound. Well, so it is making an assumption on the time bound that well every message is going to be received by within that time bound. So, if it is being sent by an honest user. Well, so the strong synchrony basically tells you that an adversary cannot control the network for long, because all the honest users are able to share the messages with each other within that time limit. You cannot create a partition in the network. Well, so that is the kind of strong synchrony assumption. So, the strong synchrony assumption helps ensuring the liveness of the protocol. Well, on the other hand, it makes a weak synchrony assumption. So, the weak synchrony assumption basically tells that well the network can be asynchronous for long. So, asynchronous for long means it is entirely controlled by the adversary, but for bounded period of time. That basically means that well it might happen that an adversary has somehow colluded a part of the network, so that whenever you have selected a committee, majority of the committee members are have been malicious or have been colluded by a malicious user. Well, so it is something like that malicious user say this is a malicious user, that malicious user have created multiple pseudo anonymous identities in the network, and luckily you have just taken few of those nodes as a part of that your committee, because you are using a random function, that verifiable random function ultimately it uses randomness. So, that is why with non-zero probability it might happen that well you have selected 8 members as a part of your committee, and out of those 8 members 5 have been selected from this colluded group. So, your majority are malicious user. Now, when your majority are the malicious user, that means the adversary has taken control of the network. Well, but what this weak synchrony assumption says that even if it happens, it cannot happen for long. Well, so there is a bounded amount of time or a bounded period of time for which an adversary can take control of the network. Well, so that means there must be a strong synchrony period after a weak synchrony period. So, eventually that weak synchrony will end and a strong synchrony period will start. Well, and what Algorand does, Algorand ensures that Algorand is safe under weak synchrony. Well, so what you can see here that it supports this FLP impossibility that we learned earlier, that in a pure asynchronous environment I cannot support safety and liveness together when there are even a single Byzantine fault or even a single fault. But here we see that well we are not assuming a strong asynchronous system for long. What we are doing, that we are saying that a asynchronous system can be for a bounded period of time. For that bounded period of time, it can be that the network gets controlled by the malicious users, but after that bounded period of time I will have a strong synchronous environment. Well, I will come out of that weak synchronous environment, under that strong synchronous environment, when I can have or I would be able to ensure that majority of the honest users are going to share the information with each other. So, the adversary cannot create partition for long in a network. So, that is something obviously a practical assumption that you can understand, that whenever certain attacks are being raised on a network, that attacks has a bounded period of time, and more than that you cannot continue with an attack. So that way within that time period, that specific time period, the attacker might have taken a control over the network, but after some time it have to release it, it will get released, and there is a strong synchronous period which is going to come, and Algorand can continue with the next round of execution in that phase. Now, with this strong synchrony and the weak synchrony assumption, let us see that how Algorand proceeds. So, Algorand, as I mentioned, that there are two phases of consensus, the final consensus and the tentative consensus. The final consensus says the following, that once one user reaches final consensus, then any other user that reaches final or tentative consensus in the same round must agree on the same block value. Okay. So, this ensures the safety of the network. So, that basically says that if one user has reaches the final consensus, that means in that final consensus all the correct participants in the network, they will agree on the same value. So, that means everyone is on the same field. Well, so that means whenever you have reached the final consensus, you can confirm a transactions or you can confirm a block. Well, that this is the final consensus for this block. So, you can commit this block to the blockchain. And tentative consensus basically says that when one user reaches tentative consensus, other users may have reached consensus on a different block. So, that different block may be a correct block. So, this is some scenario which is similar to fork. Well, so in case of fork, we have seen that there are different blocks which are getting committed, both of the blocks are valid block, but both of them got committed eventually. But here what happens, that that particular scenario in Bitcoin, when a fork is being generated, that means a part of the users on network, they have agreed on one block and part of it has agreed on a different block. That scenario we call it as a tentative consensus here. Well, so this tentative consensus can be in two cases, when the network is strongly synchronous. So, when the network is strongly synchronous, then the adversary may be able to cause the Byzantine agreement protocol to reach tentative consensus on a block. Well, so in that case, B star is unable to confirm that the network was strongly synchronous. Well, and when the network was weakly synchronous, during that time, B star can form multiple forks and reach tentative consensus on two different blocks. Well, so the users are split into groups. So, basically under a weak synchronous assumption, what might have happened that the adversaries have partitioned the network. When the adversary has partitioned the network, one partition of the network has agreed on one block, another partition of the network has agreed on a different block. Well, so that is in the case of weak synchrony assumption, and we have reached in a tentative consensus here. But whenever the network is strongly synchronous, during that time, it might happen that a single block is still in a tentative consensus, because the Byzantine agreement protocol, which is running at the back end, it is unable to confirm that the network was strongly synchronous at that point of time. So, then you have this tentative consensus. Now, the question comes that from this idea of tentative consensus and final consensus, what we understand that if you somehow reach to a tentative consensus where the entire network has not agreed on a single block, rather a part of the network agrees on one block and the part of other network agrees on a different block, then I have to somehow come out of that tentative consensus. Well, so to come out of that tentative consensus, what you do, that you run Byzantine agreement periodically to come out of this tentative consensus. So, as I mentioned, that network cannot be under weak synchrony all the time, and cryptographic sortition ensures that different committee members will be selected at different round of the B star. So, assume that you are at round 1 of B star. Now, at round 1 of B star, so you are selecting say 10 committee member. So, whenever you have 10 committee members and you are running B stars, so assuming that 6 of them are malicious. Now, when 6 of them are malicious, then you will reach in a tentative consensus. I am running it at TC. So, when it is there in the tentative consensus and part of the committee members agrees on one block, part of them are agreeing on different block, that kind of scenario is there, then this timeout occurs and you move to the next round of B star. So, the round 2 of B stars. So, in round 2 of B stars, again you select a member with 10 committee member, but this time again the cryptographic sortition is getting executed. So, cryptographic sortition is going to select different set of users as a committee member. Now, when it is selecting a different set of users as a committee member, it is unlikely that again majority of the committee member is going to be malicious. Well, so that way at that time it might happen that the majority of the committee members are correct committee members. So, you are being able to reach to a final consensus. So, that way until you are running getting final consensus, you keep on running this cryptographic sortition in round, and whenever you are running cryptographic sortition in round, different round is selecting different committee members through this verifiable random function, and eventually you will have a committee which will help you to reach to the final consensus, and that is the kind of magic which is being done in Algorand. So, the Algorand basically ensures that by repeated execution of the Byzantine agreement protocol on top of a randomly selected committee member, we can reach to a final consensus. And what they actually mathematically show that you do not need to run this Bierstadt's algorithm for multiple times, not for 10 times or 100 times. So, 2-3 times are sufficient for most of the cases, even if around 49% of your participants are malicious. Well, so that way we see that we can run PBFT or rather BFT or Byzantine agreement protocol in a scalable way with the help of Algorand by introducing this concept of cryptographic sortition with the help of verifiable random function. That clearly makes the system much more scalable compared to the existing work. So, this is the kind of overview of the Bierstadt algorithm. So, you reduce the size of the network by using cryptographic sortition, you run the Bierstadt. Okay. So, we are calling it as a binary Bierstadt because it is taking a decision whether to accept a block or reject a block. Then you count the votes, your number of votes are equal to the binary Bierstadt result. Then you are in a final consensus, otherwise you are a tentative consensus, move to the next round with a new set of committee members. So, that is the kind of entire algorithm which is being executed. So, in conclusion, what we see that Algorand has multiple advantages. So, it provides Bitcoin like scalability, it provides BFT like throughput, but without having any fork in the system. Well, so it can alleviate majority of the problems that we have seen till now. But one point of caution that we need to keep in mind, because there is no free lunch as we have mentioned earlier. So, there would always be certain kind of trade off. So, the trade off of Algorand is that first of all it needs a really large network. If you run Algorand on a small network, then cryptographic sortition is going to select very small set of committee members, and it will be possible for a attacker to attack on that small set of users. So, that way we need to have a really large network to have this cryptographic sortition run correctly. And on the other hand, you have seen that regarding the network, it makes an assumption that an adversary cannot hold the network for long. Now, if you have a scenario, if you have an application where there is a possibility that an adversary can hold the network for long, then possibly it is not a best choice to use Algorand kind of algorithm there. So, that way, as I mention always that whatever mechanism we are going to use, there is always some kind of trade off, and we need to keep in mind those trade off and accordingly select the best mechanism for the problem that we are going to solve. So, that is all for this particular lecture, and also we conclude our discussion on consensus mechanism on blockchain. In the next lectures, we are going to start with some new topics that would be taken up by Professor Shural. So, see you all later on. I will be coming back with the discussion on different use cases on blockchain. Thank you all for participating in this course. See you again. Bye bye.